Hello everyone! Today I will continue the big topic of electricity with the next lecture, which is called capacitance. And today we will speak about capacitors and this property, capacitance. And of course I will write something down. And first I can already write down the topic. Capacitance. That's it. So, what is the idea? In our electrical circuits, we have such a component which usually looks like this. This is a typical visual picture or schema for a capacitor. Capacitor is an element which consists of two plates and a distance between them. This distance can be filled by some dielectric or another material, and depends on the material. It will be important to know how much charge is collected, yes, on this capacitor. So this is also my doggy, Socrates. Stay calm, my dear. Yes, Socrates is very interesting in physics, you know. Socrates. Yeah. All is good. Okay. Socrates. Good boy, Socrates. Huh? Okay. Stay with me. Okay. So we will continue. And now, in circuits, usually we don't use exactly such a capacitor with two plates, two sides of plates. We use another kind of capacitors which look more like, it is called Swiss roll. Yes, I have already googled what does Swiss roll means. Yes, it's like a cake, very tasty, and with two wires on the top. Yes, so in such capacitor, one of the plates is replaced with electrolyte, and that's why it's more compact and we can use it in a better way on our circuits. That's it. And capacitance. Yes, capacitance is a property of a capacitor which shows how much charge can capacitor store per volt you need. Yes, I'm living near the farm, so you can see a lot of tractors riding around. But don't worry. Now I will write down the formula. So yeah, in such situation I live usually. Okay, so this is our formula, yeah, where Q is charge. Yes, charge usually is counted in coulombs. Here is C, this is our property, capacitance. Yes, capacitance. And V is voltage. Voltage is counted in volts. It's easy. And capacitance is counted in farads. Usually 1 farad is a very big unit, so we use microfarads and nanofarads. That's it. So now we will see what is going on when we really have the capacitance in our circuit. I need to to draw such kind of circuit. For example, we have something like this. Yes, I'm drawing circuit to you. We also have ampermeter. We have resistance. We have here is a capacitance. The sign is old, even when now the capacitance you have already seen is looks like a roll. And here is voltmeter. Yes, usually voltmeter connected in a parallel, and ampermeter connected in a row, I can say. Yes. So here is C capacitance, and we have a direct current supply. This direct current supply usually draw like this, and where we have the bigger, yes, we can say line, here is plus, and where we have the shorter line is minus. So this is our one of the popular way how to draw the schema of capacitance. Yes. And usually we have resistance all the time. It means that even if we don't want to put the resistance in a circuit, we have it, because usually our wires have resistance anyway. So we can collect all the resistance of our wires just in a one sign and do something like this. What is going on when we put the capacitor without a charge into the circuit? And this is the circuit, as I said, with direct current supply. So electrons begin to go from minus, so all electrons, yes, state near the minus, I can say, yes, and they begin to flow to a capacitor. Also a nice moment, you can hear the big birds, yes, clucking, clutching, or how to say, yes, that's very nice. And so that's it, yeah. Socrates want to say something, yeah, Socrates, yeah. Very nice. So that's it. What's going on then? Yeah, Socrates, do you know what's going on? He don't know, but he's happy. Very happy dog. Okay, Socrates. What can I do for you, Socrates? Maybe I can give you something. Yeah, Socrates? Huh? Ah, he likes glows very much. So he will steal my glow now. So what's happening? All this negative charge is collected on the one of the plates. And on another plate, yes, gathered positive charge. And all the negative charge gone from the second plate this way. So this means that when we have this flow of electrons, current goes. And this is the point when the process of charging the capacitor started. So capacitor began to charge. As more as it charge, a less current can go towards the capacitor. Because more electrons come in, yes, and gathered on the one plate, and there is no electrons more to go away. Yes, because here is no connection, here is something like a distance, yes, we remember that. That's it. So what can I say more? And when the capacitor is fully charged, it began to have a voltage the same as the voltage of direct current supply, and there is no current flowing anymore. That's it. That's how it works. And also we can paint graphics. Yes, what is going on graphics. Usually we have a graphics of current versus time, and graphic of voltage versus time. Yes, you can see it here, maybe not so good looking. Okay, and now I will draw them. So what's going on? For current, at first we have a big current, and our initial current, we can say our initial current, it is voltage divided on resistance. Exactly voltage that we have from our direct current power supply divided on resistance that we have in our schema. And it goes like this. So, yeah, we have something like this. And what about the voltage? We have some number of voltage, which is the same as voltage on the direct power supply. And the voltage on the capacitor began to grow like this. So that's it. And when the voltage of the capacitor is the same as voltage on the direct current power supply, the current drops and there is no current anymore. So we can say that we have this time delay. That's also how the capacitors can be used. They are used in schemas when we need a time delay. For example, we need a time delay to switch light bulb. For example, we can have a light in our car, and when the door is closed, the light not exactly at the same time is closed, but it delays in several seconds. It is called courtesy car lights. So in such schemas usually used capacitors. That's how the capacitor charging. So charging a capacitor. Yeah, that's how charging a capacitor. Great. And now we will see how to discharge a capacitor. You can see that I live near the very popular road, like in the city center, downtown. It's a very, it's a firma where one of the popular brands of milk in Belarus produced. It is called Savushkin product. So that's it. And you can sometimes see labels on the cars. And I continue. So I will draw there something like the same. I will draw the same schema, but without direct current power supply. Just ampermeter. For what? Here's ammeter. It's called ammeter. I usually called ampermeter from like a Russian version of all of these. But in English, I discovered it's ammeter, but not but Okay. Here is a voltmeter, and what does it mean now? I can say that discharging of capacitor. Yeah, discharging of capacitor. So our capacitor is already charged. So as it is already charged, it begins to discharge. And here we had more electrons, remember about that. Yes, we have negative charge on this plate. Here we have positive charge. So now the capacitors runs like a direct current power supply, but in the opposite direction. So we have a current flow like this. So current begins to flow in the opposite direction, because of course now we discussed only about how electrons flow, but exactly the direction of current is in the opposite way. Anyway, it changed its direction. But now we speak about exactly how electrons flow, yes, to be more correct. And we will have this current flow until the capacitor will be completely discharged. And we can draw also plots. This is the plot of current versus time, and the plot of current versus time will look like this. So yeah, and here will be the initial current. Initial current is the voltage that collected on the capacitor divided by resistance. Our resistance, this one. So it's Ohm's law. Yes, very popular Ohm's law. Okay. And you can, yes, we can notice that current painted not from the top, but from bottom, yes, to top. It means we draw like that because our current changed its direction. So we can somehow draw it like the current have a negative direction now. So this minus means only changing the direction of current. The amount of current is the same, yes? And we will have a plot for a voltage. So voltage versus time, yes? Voltage versus time, you can see it. And for voltage versus time, yes, we will have something like this. So we have this voltage of a capacitor. Yes, capacitor was charged and have some amount of charge now. Yes, so it can provide a voltage, and it's discharging like this. So the main idea is that it's not straight line, it's like this. Yeah. Okay, so we have talked a little about what is a capacitor, where it can be used, and what does it mean to charge the capacitor and discharge a capacitor. Also, now what can we do? We can see how don't know, do we need to speak about this now? But we can, yes. For example, in our schema, we have seen a resistance, yes? So resistance, you have seen the resistance. So it means that how the resistance depends on the amount of current, for example, or amount of voltage that we have. So we can draw that, yes? I can draw, for example, two plots. Yes, that's plot of current versus time and voltage versus time. Yes, two plots. And as we talked, yes, we can draw a line. Yes, for example, for current, yes, it's for charging. For current, it will be like this, and for voltage, it will be like this. Yeah. For example, if we want to put some resistance which is lower resistance. So for lower resistance, the situation will be like this. It's lower resistance. Yes, we can see that this plot changing a little. So I can put that low R, and here I can put low R. Yes. So green will be more higher resistance. Yes, and also we can draw for higher resistance, yes. So higher resistance will have like this and like this, yes. So we have higher resistance, high air, yes. So what does it give to us? It gives to us that we can change a time, a delay of charging a capacitor with changing the resistance. That's very important. And also, yes, doggy is coming. Huh? Do you like it? Do you like it? Do you like it, Socrates? Okay, he likes. So we can see the process. Of course, for uncharging, it will be looks like this. Socrates, дай мне. Socrates, huh? Sorry, I need to call my dog because he likes to go away for a long time and difficult to find him. Eat him. Okay, please stay with me. Where is my glove, Socrates? Where is my glove, Socrates? Huh? Another glove. I need to give him another glove. And now I want to draw what will be the difference if we will change a capacitor. Yes, capacitor with another amount of capacitance. So we can also draw for charging process, for example. For discharging, it will be very looks like similar way. So here is current. Here is time, here is voltage, here is time. Yes, you can see that. So, so it will be looks very similar. We have, for example, like this plot, yes, initial current, and we will have like this, yes, and so like this it will be a more lower capacitance. So we can also low C, yes. And for this it will be higher capacitance. So higher capacitance, yes, something like this. High C, yes, you can see that. Great. So also changing the capacitor, we can change the time delay. That's also very important. Okay, so I also showed you how resistor and amount of resistance and how capacitor and amount of capacitors change the current flow and change the voltage, and how we can use it and where. Okay, and maybe at the end of our lecture we can resolve some physics problem. So I have a big notebook where I have written different problems and want to use one of them. Maybe not very easy, but not very difficult, but not very easy at the same time. Okay, let's do like this. So I will read it and then I will resolve it. A problem. A capacitor has a capacitance of 250 nanofarads and is connected to a power supply with a voltage of 12 volts. Yes, here you can see my problem. Yes, with the salvation. Yes, okay. With the resolve. Okay, it will come and we will continue. And we have a question. So we can write down that we have a capacitance, our capacitance and our voltage. Yeah, I wrote it down. Yes, we need to find what will the voltage across the capacitors be when it is fully charged. So when the capacitor is fully charged, the voltage will be the same as on the power supply, so it will be 12 volts. So we can call that on the capacitor 12 volts. So it's easy, yeah? The next question. Calculate the charge stored by the capacitor when it's fully charged. So calculate the charge stored in the capacitor when it's fully charged. We have this formula and we will use it. So it's 250 10 in minus 9, yes, multiply 12 volts. So it will be, I have already counted, it will be 3 10 minus 6 yeah, minus 6 coulomb, and we can write it as 3 microcoulomb. So it will be our charge, yeah. So it's easily only the one formula. And a little bit more difficult question. The capacitor discharged in a time of 9 seconds. Calculate the average discharge current. So we have that time is 9 seconds. We need to calculate the current. We know such a formula that current is the gradient of charge. So it's how charge changes. So from that we can use this formula, yes, and we can put CV, yes, and we will have the full formula from all that we know, or we can already use the information that we have counted in the previous question. So we can use 3 10 minus 6 divided by 9, and we will have approximately 0.33, and it's endless 3 microampere. That's it. So that's how to say, not very difficult task. It's one of the typical, and we solved it. Of course, if you have more tasks and want my help in solving tasks, please write me. I will try to help. Okay. And so for today, that is all. Thank you for listening, and I will thinking about what to tell you the next time. Okay, thank you. Goodbye.